Welcome you all. Appreciate you coming up for class 9 here. I am going to record this. There are a few people that are going to be not being able to join us. It may affect your teamwork. We'll figure that out when we get to the team exercise. By the way, I just came off an 8 hour or 8.5 hour. It was 8.5 hour course class I had to be part of. I was a student like you are now, and so I am a little frazzled slightly. So if I do kind of move too quickly, and you don't actually understand what I'm trying to say, please unmute yourself and say, "Hey, professor, could you go over that?" Or just ask your question, and I'll try to be more specific as I go into each of the slides and the points I'm trying to make. I'll also try to keep an eye on the hand raising, but the slides in front of me, so I may not see it. It may be better if you unmute and just say, "Excuse me," and I'll stop. Um, because I tend to really keep going and going and going, and just kind of the mode I get into at times. So stopping me in the middle of something is more than welcome. All right, with that in mind, our quote of the day kind of comes from a book I actually looked at to think I was going to make the book part of our class. I decided to go with just the system engineering book of knowledge and things like that instead. But what I liked in their intro is their explanation of the importance of systems integration. He talked about how dreamers might envision the future, but it's the pragmatic people who actually build it, right? To solve the right problem in the right way, that's what moves mankind forward. And to solve the right problem in the wrong way, or the wrong problem in the right way, whatever, even if it's clever, even if it's ingenious in its solution, it doesn't help anybody. It doesn't credit mankind at all. So instead, this misfire demonstrates a failure to appreciate that crucial step in pragmatic problem solving, which means system integration. Now, I don't know how many of you may have spouses or something, but my spouse will actually tell me what her problem is, and I try to run into that pragmatic systems integration. This is what it's going to take to do it. Sometimes you just need to listen. I'm just trying to help you out. If you do have significant others, don't try to solve all their problems. Just listen, and maybe they might ask you to solve their problem. Then you can start getting into it, but don't do it automatically. I know as engineers that is something we tend to do. All right, let's go to the next one here. We're at after the midterm. A lot of you finished the midterm, did very well. As you can see, this class, it does take a while going and to understand kind of the rhythm and to get your points up. I give you a lot of chances to get your points to the point. I think most of you are in the A-B range right now, and you'll continue to do that as you do your homeworks and work your last team project. So that should work well. So this class, what we're doing now is getting to the other side of the V, or the bottom of the V, and I'll show you that as we move along here. But it's integration. You know, what does it take to actually build the system? So at the end of this lecture, you'll understand how that you're assembling the actual implemented elements that we talked about several classes ago, and you're actually trying to create that whole system that you originally designed back in your design phase. And of course, this is where we're going to actually look at the objective of the integration progress. So we'll go into that looking at the ISO 15288 view of integration. And we're going to actually talk about integration enabling systems as an exercise. It's just a good way for you to kind of think through what you would need in order to make your function for your product put together. And also in the last part, because part of integration is actually interfaces. And so we're going to get into N-square charts and how that works. We already covered N-square charts just slightly in terms of how to look at N-square charts, how to add them up to see if they're good or not. Now I'm going to show you how to actually do your analysis on N-square charts and how to reduce that number that you get when you actually add up the N-square chart. Okay, so again, if it looks like I'm kind of misstepping or not explaining the concepts, please stop me, and I'll go back. All right. So what I want to talk about is implementation. Basically, what we've done right so far is we've actually gotten to the point where we now have some development requirements. We went through understanding the mission. We've gotten down and tried to get all the stakeholders involved in terms of understanding their needs and requirements. Once we had that, we were able to kind of visualize and document an actual system that in place. And we also, from there, we were able to break the system out, get the decomposition happening, and then come up with what we call configuration items. So once you have a configuration item, you have a requirement or a spec that you can give to someone to actually develop that item, or you can buy the item if you have to. So a configuration item, that's kind of a, it's kind of at the level where you can actually say, hey, now I can push this off to somebody to actually build. So it usually has 4 characteristics you want to think about. One, it should have a very specific defined functionality. This configuration item does this one specific thing, right? And of course, it would work within your functional architecture and your functional decomposition that you did when you did the design of your system. So you have a defined functionality. Also, you should be able to take that functionality in that configuration item or that element, and you should be able to replace it as a whole entity. So they usually call that the lowest common module that you can, or replaceable module that you can take out and put a new one in. I always think of it, if you want to kind of have some visual aspect to it, think of it this way. I have a hard drive within my computer, and when that hard drive dies, I can buy another hard drive at Best Buy, come in, take that one hard drive out and put the other one in. So actually, computers, desktop computers, things like that, a lot of those elements are replaceable, even the monitor and things like that. So you have defined functionality. It's very easy to replace the entity with another entity of its same sort, because the unique specification of that entity or that configuration item is such that you can give it to 1 or 2 or 3 contractors to actually build the system in accordance to its spec, and it can be replaced as we're doing there. And because of that, you control your form, fit, and function of that element as you move forward. And then there is an aspect of enabling systems. Those are the aspect of your software development environment or your hardware manufacturing tools. We get into that a little bit more when we get into your exercise. And then there's the aspect of when you actually build your system, are you verifying that component? So be it software unit test or an actual hardware conformance, how is it working with the drawings and things like that. So again, there's an aspect that you could either build or you may buy that configuration item. So a lot of a lot of system developers actually get into this whole buy scenario where you now have a very specific understanding of what you need. You go out and find who's actually good at doing that. One of the examples I give is if you're Boeing and you build airplanes, and Federal Express comes to you and they say, we want you to build an airplane for us, then you would actually go ahead and try to build what they need. Now, in there, you need an engine. Well, Boeing's not famous for their engines. And if they were trying to build their own engine, they probably wouldn't be good at it. Now, they would go to someone like Rolls-Royce or General Electric, who actually build these engines as a matter of course. It's part of their business model. So you would actually go out and go, here's the engine I need you to build for my new Federal Express airplane. And you would give them the spec, they would build it, you would get it back, and you would integrate it into it. So part of getting them to understand what they need to build, you prepare this acquisition proposal, you send it out there, and the various suppliers, be it General Electric or Rolls-Royce or Pratt & Whitney, whatever, they come back with a proposal. This is how we would build it. You would actually go ahead and initiate agreement with one of them, whichever, because you would actually review their various proposals to see which one was the best. And you would initiate an agreement, monitor that agreement, and then eventually they would give you that engine for you to test and make sure it meets your specifications that you gave them. So that's the whole aspect of buying the configuration item. So, and part of the other aspect of this is and that's actual elements that you would buy, but the actual implementation would be if you actually had to also build the system element yourself. So that's something that you would have to do. So you would prepare the implementation, perform the implementation and management. So this comes from ISO 15200. What I actually done is I've actually taken this from a class where I teach the entire INCOSE System Engineering Handbook, and I actually show you the actual inputs and where those inputs are coming from. So if you remember my first, I think second lecture, I gave you this huge diagram that kind of showed where implementation stood and what the other processes do. So I'll let you read this on your own unless you have some questions on that. But the actual process itself is actually preparing the implementation, defining what your fabrication and coding procedures are, so that when you actually get into the implementation process, you're ready. So you plan, you document it, and then you actually perform the actual implementation, where you actually take that spec that came from the actual design activity, and you actually start building to or coding the actual software component according to the documents you've been given. And of course, at this time, you also think about, well, what kind of training capability do I need for this element if it is a large one, or if you have several elements that have to come together, you may have to think about that as well. And then, of course, there's packaging and storing the various elements as you finish. And then you actually, after all the elements have been built, you have to manage those elements, maintain their records. Any anomalies that are there, that should be inform the integration people. And then the traceability of that element back to its configuration item specs and back to the actual design within the entire system is a traceability that you continue on as part of this process. So your outputs, of course, would be your strategy, which would help you up front. But the main thing you have is the actual system elements themselves would be coming out, and that would be falling into integration. And of course, everything else is important as well, and as well as the enabling system requirements. And we'll get into a heavy dose of that in a while. Here's some common approaches. One of the things that a lot of companies do is they have a product development team that help kind of develop that configuration item, getting it to that point. And so they actually are a good one to keep together when you get to the actual implementation, because they understand the product more than probably you do. So having them involved in order to maybe see if while you're implementing, if you run into any problems, you're able to pull on their understanding in order to solve those problems. There are conformance audits that are very important, especially from a hardware where you're verifying the drawings, or software where you're verifying that the software will perform the way that you expect. And there are times where you actually have to have simulations for the other system as a whole. And so while you're putting this one part into that system simulation, you can see if the system that element will react correctly. All right. Wow, I just talk on and on and on. Is there any questions whatsoever? And I know I'm such a good teacher, you probably don't, but you never know. Always throw it out here in case you have anything. So I'll wait a few seconds to see if that'll work. Anybody? All right. Give me a thumbs up just so I know you're there, or a high five or something so I know you're alive. Raise your hand like I'm doing. Okay, good. Okay. A few of you are there. It's 3 of you. The rest of you may not even be listening. Oh, you got it. Okay, good. Okay, good. You can lower your hand. That's great. That's great. Thank you so much. All right, let's get into some implementation concepts. One of the things is the actual aspects of understanding your system elements, what forms they're in. Like, for instance, you may have hardware or physical pieces that you're bringing together, and you have to fabricate that hardware and put it together. Or it may be software oriented, where you have to have coding and certain executional aspects that you're working. But you may also have, and this is something that a lot of times are overlooked, is you may have operational resources that are elements that need to come together. Like, for instance, operational procedures or operational training. Those things have to be prepared as well, even though they're paper products or PowerPoint slides or whatever. They still need to be made, and they still need to be thought about in order to get ready for the system to be integrated and eventually in the operational field. So your implementation process will support that creation or the adaptation of whatever elements you're bringing to bear to make this huge system. So you usually have a system element that may have been developed by somebody else, and you adopt it into your system, or it's a newly created product or element, and then you adopt it once you're finished with the actual implementation. All right. So part of that is kind of understanding that you have some detail, high-level requirements that you would actually use when it comes to integration. Now, remember, we were down here at implementation. We're going one step further up. And on the right side, that's where we actually integrate and create the system. But on the left side, you still have those requirements that kind of guide you into what you're building as you're doing that. So integration brings those elements together, and there's some element integration enabling tools. Sorry about slipping on my tongue. There are tools and equipment and technology constraints, all which come into play as you're doing this. And of course, while you're doing this, interfaces become super important as you're working this. And don't forget, you can verify each element as you're about to place it into the larger system through the technical performance measures. Those are kind of your ways of knowing that element will indeed meet what is necessary for the system as a whole. So these are the 15288 view of integration, various inputs coming in, especially over here. You'll notice the system elements and the various documentation, as well as here from acquisition, you're bringing in elements that were bought. So both what were built and what was bought are coming in, and you actually perform the integration here. Of course, you prepare for it beforehand and you manage the afterhand, but the main output here is your integration system and element. Your integrated system, I'm sorry. So these are your inputs. I'll let you read those later. And these are the actual aspects of preparing for the integration, looking at your constraints, doing a good aspect of planning it out, and making sure you have those enablers that help you make sure the integration can be done. From there, you actually perform it. You assemble those verified, validated system elements, and you make sure they give you the architecture characteristics that you actually put into the design aspect of your system. And of course, once you're done, you now have a complete system. Now you can actually record the results of this integration, maintain the records, and record any anomalies that may occur while you're doing this. And your outputs, your main output is your integrated system and system element here, which actually is now flows into verification, which we'll talk about next week. There is some common approaches and tips about getting your integration strategy up front and understood so that the planning and the actual execution of the integration will go a lot smoother. Making sure you have enablers in place. And if you have to develop any enablers, identify them way up front so that you can actually make sure they're ready when you are ready to do your integration. And of course, integration from a scheduling standpoint, it's important to have some kind of buffer. A lot of times your actually design work and your implementation can kind of really draw out longer than you anticipated, and it starts shrinking your integration window. If you could just move the integration window, that would be even better. But program managers usually have different ways of thinking that way. But it would be good if you actually work that. The other thing to think about, and we'll get into detail here, is integration of an aggregate, where you actually take certain system elements that make up your subsystem. So you could have a system that has various subsystems that have various elements, and you can actually perhaps build that subsystem separately and aggregate the things up. And as you do that, you can actually perform verification actions to ensure that system element will indeed perform the way that you need it to perform from the system level. So that's why you do this integration level by level, integrating from the bottom up, making sure each element works as you do each subsystem, making sure that works, and then integrating it into the larger system. So there are different strategies and approaches that I like to talk about here. Some of those techniques, just to let you think about. And by the way, you don't have to just say, oh, we'll just do this one technique. You may find yourself using 2 or 3 of these techniques. Like, for instance, you may find yourself one of these techniques is very helpful from a subsystem standpoint, but from a system standpoint, you may use a different technique. So as you look at these, try to think about how they would be utilized. What are the pros and what are the cons as we're coming together? So one is global integration. Let's just put it all together and hope it works. Now that is nice, big brain. Your systems are all done in one step. It could help you with your schedule, and you don't need any simulation as you're going along. But the problem is, if it doesn't work, how do you actually detect and localize those faults. And it's a lot more complicated. Of course, you could build the system to kind of see those integration and faults that are there, but you are complicating the entire venture that you're trying to accomplish when you do this. So simple program systems, or systems that have been similar systems you built in the past with, yes, you could do this. But if it's a complex system or something that no one's ever seen before, you may want to look at these other integration techniques. One is integrating it with the stream. In other words, as each element is developed, you actually take that element, put it into perhaps a larger simulator, and make sure it works within the larger. And as another one gets done, you put that one in, and before you know it, your simulator slowly but surely gets replaced by the actual system itself. The other one is integration, implementation. In other words, you take one or a few system elements and you actually put them together as kind of larger elements or subsystems. That way you can kind of, if it doesn't work, you can localize and find where the faults are a lot quicker. And your simulators will be required, but now you're using it in a larger sense. Subset, again, where you do aggregates of subsystems, and you do these in parallel, test them out, and then put it all together. Top-down integration is an interesting one. If any of you have ever worked with a software language called Ada, which is kind of out of fashion right now, but that had a very nice top-down integration approach, because you could have a shell of a program that had the interfaces in place with stubs to the various functionalities you need, but you could make sure that the integration at the top level was working because your integration interfaces were in place. So that's one thing you could do. You could actually design your system to actually allow you to do that. The other one is bottom up. You just kind of take each element, test them all, put them together, and do it that way. The other one is criterion driven. That's basically just looking at your system and saying, what is the most difficult element to build and to integrate into this system? So you may be Boeing and you say, you know, that engine is going to be hard. So you contact Boeing and have them do it quickly, and then you integrate it with the wing and other things rather fast, so that if you do fail, you have time in order to go and make changes as you want. The other thing is looking at your organization from an N squared standpoint. Look at that matrix and try to figure out which are the best modules to go first in order to see if there is any fault detection or fault aspects that you have to worry about. So anyway, those are different strategies and approaches. You should be able to look at the combination of these approaches in order to figure out which is the best for your system. So the other thing I want to talk to you about is the system build. There are various highlights here, or steps you do. It's almost like if you were hired off the street and they said, build this system, integrate it. You know, you're like, oh, what do I do? Well, here's your steps. You figure out your system hierarchy, get your interfacing components and subsystems, and then you look at your functional and physical interfaces. You start working off those and actually start organizing your interface control documents, work with whatever groups like integration or product development teams, and work with them and your interface working groups, review those test procedures, audit your designs and your interfaces. Then you ensure those interface changes are incorporated into the specification that you find. So that's a good way for building the system by itself. The other thing is, how do you make sure that system, once it's built, is working within the external systems? Pretty much the same thing, obtaining the data, defining your system structure, and the interfaces that are external. obtain those interface control documents and make sure those interfaces are ready for your system to put together. So your interface control document is one of your more important aspects of what you try to work on. And you work with a interface working group to make sure that your interface document is correct. So the whole idea here is you're working with another external system, making sure that your system will work with it. Now, that means you are working with them and they will modify or change their interface to accommodate your interface. Now, a lot of times the companies or a project will have an ICD and say, this is it. You build to this interface control document. So you wouldn't negotiate with them necessarily, but you would take their ICD and it would become a spec for you to make sure your interface is done correctly. There are some pitfalls when you go about doing this with your interface and trying to work the various things, especially when it comes to delays that occurred because you didn't quite understand the complexity of putting all the system elements together, especially if you're trying to do it with a big bang approach, which is really not appropriate for a very complex system. And of course, you plan your integration too late, you may actually not have the integration elements or enabling elements in place to help you go through this. So start thinking about your development early as a means to make sure you have everything in place. Think about those enabling elements that you need in order to make sure your implementation goes well. Use a coupling or an n-square matrix for your interfaces, and always be flexible with your schedule, but try not to have your implementation deadline stuck at one location on your calendar. If there's problems further up the stream, push it out, because you don't want to say, oh, I have 2 months, and then as everybody slips, you start getting from 2 months to a month to 2 weeks, and that's not good. Integration and design teams should always be part of your design work. And these are aspects to integration, various principles you could use, such as aligning your system to the strategies of your business enterprise, being able to partition the elements in such a way they're traceable, the induction principle, where you're using very inductive reasoning in order to figure out what your integration strategy is, the principle of limitations, understanding whatever your integration is only as good as what your architecture has been capturing from the shareholder requirements. The principle of forethought, where you actually kind of think through this whole aspect of integration, not waiting for the last minute. So planning becomes a very important aspect of that forethought. And then the principle of loss, where a lot of times you have to give up certain behaviors that you would like your subsystem to have, but the greater whole will assume that actual requirement or functionality. All right. Any questions? And if I could get another high five from you guys, we'll high five each other from you. Thank you, Jordan, Precious. I appreciate it. Good. You're all awake. Thank God. Okay. Whew. All right. We'll get you out of here. I might get you out early today, so we'll see what we can do. So with that in mind, what I want you to do now, I may have to put you in different things. So tell me what teams are available. It looks like I only have 1, 2, 3, 4, 5, 6, 7, 8 people out of the 12 I'm supposed to have. Look at your teams. Do me a favor. Go into your chat and tell me what team you're in. Let me put the chat out. Where's the chat? Always have, oh, there it is. So conversation. Okay. Tell me what team you're in and how many team partners you have. Because I may have to put some people in other teams. So do that for me real quick. Okay, Precious is by herself, so I think I may have to give her to one of you guys. So what other teams are out there? Sorry, Precious, you're going to have to catch up on whatever function that they were working. Nosh, Sev, Alden, any of you? I know you're probably typing up. I'll wait for you.
I'm sorry. I'm a bit confused. What's going on?
I'm sorry, Alden. I was explaining I want you to type in or tell me personally who's on your team and do you have all your teammates?
Oh, I think we have Nasher and Marcus. I'm not aware that they dropped the class or anything. I don't think
No.
they
You should be looking at, do you see all your people? You should be able to
Oh,
show participants and
okay.
see who's here. So
Okay.
go, yeah, got it? All
Yeah.
right,
You're talking about now. I thought you were talking about
right now, because we're about to do an exercise. I want to make sure everybody has their teams. All right.
Yeah,
No,
my whole
it's just
team
me.
here.
You're okay. Who was that? That was Nasher?
Auden, or it's me and Nasher. I'm sorry. Marcus isn't here.
All
We're
right.
missing one.
And Jordan, you said you have everybody?
Yeah, I do.
All right. And who are your people? Sorry that I don't remember.
I got Hashim and Jay.
Okay, good. And Alden, you have Nasher. So Sheev, and Rohit, are you there as well? Rohit, you can come online. Are you even there, guys? Did they just kind of log on and leave? Yay. Okay, may not want to talk to me. That's fine. So Precious, if you don't mind, there you are. You're probably having trouble with his mic. Can appreciate that. Let me go back to your conversation, see what you said. Okay, good. Team 2. Would you mind, Alden, we'll go ahead and get you and Nasha. Which team are you again, Alden?
We we are team 4.
Team 4. I'm going to give Precious to you. So I'm going to go into your team structure and put Precious in there so she can go ahead and be part of your conversation as you're doing this, okay? And try to welcome her and make sure you you can explain what your system element is, all right? So what you're going to do as a team, get together, think about your actual system function that you're pulling together. And as you integrate the actual pieces in order to make that function work, now remember, it's more like a subsystem that you're building for your pomegranate. But I want you to think about, well, what kind of enabling systems do I need to make sure that I can integrate this thing together? Okay. So that's what I want you to think about, and then we'll have you guys type it up on your actual systems as you do that. So remember, over here, you should be able to go, and I'll put Precious and Manage into Team 4 here. Go ahead and start a new conversation and go in there and start working on file. I think it's class 9, exercise 1. So go ahead and pull that up and start brainstorming about your actual enabling system. Now remember, enabling systems are things that help you do the actual function of integration. So integration, you're like making pieces come together via interfaces or things like that. So what are those enabling systems that you would need to make your actual function work? And you may want to kind of describe your function. It's been a while since we've done this. So you may want to actually describe. okay, as you're doing it. All right. Okay, go. You guys, I'm going to give you till let's do 5:40. 5:40. We'll start up again. And so I need you to finish. If you do finish early, just get back into the general one here and let me know you're done. And if so, maybe we'll go ahead and finish this up earlier today, because I have one more exercise I need you to do. All right, you guys go ahead. It looks like team two's already in there. Let me go ahead and let's get started here. Let me pull up the right one. Here we go. It looks like we have Alden. You're back, maybe. What team is back? That's Rodent and Shape. You're team
Team
two.
four.
Team four. Team four's done, right? Okay, good. Precious liked it. All right, well, let's go in order here. Let's just go with team two. I think team three is done. Okay. Okay, Alden, you're still in that one. Okay, good. All right, let's go with each one here. And not to push you along, but I have one more area I want to kind of spend a good amount of time to make sure you understand it, because it's important for your homework. But let's get through this. The whole idea of enabling elements for whatever phase or process that you're in the middle of is very important. So let's start with, and just tell us real quickly what you guys were in terms of what you're doing. I believe you're the language translators, right?
Yes, we have a voice translator in our Pomegranate system.
Okay.
So our integration animal systems were enterprise application integration, which is like application developer operations. Then the data integration, which for which we'll be using a data integration tool, like a cloud service or something like that. Then electronic documentation service for the
Okay.
integration of different languages, a voice note compiler, and a translation API like the Google Voice Translator uses, or like an AWS service.
Okay, tell me how a voice note compiler, that's actually interesting. What are you thinking there from an now remember, integration is taking the pieces and putting them together.
Yeah,
So
so that's how the words get combined together when a user speaks. I think that's
yes, okay, that makes sense. And
I
the
mean,
electronic document integration and interchange?
Yeah, so when we mean voice note compiler,
Okay,
we're also talking about the electronic document integration.
okay.
So within the document integration of different languages, we're also going to have the voice note compiler to use that to integrate the voices
Oh, no,
that
no,
are spoken.
okay.
Yeah.
Oh, no, you guys thought through this. That's good. Because I know how difficult it can be when you're talking about something that's so software centric. I mean, you
Right.
still have to make sure it works within the um, kind of the confines of your chip and the way that works, but your processing, right, to make sure it works. But I see what you're doing. You're trying to integrate all the various components of the
And
software
yeah, into one.
into the larger system. So that's
Yep.
where your cloud service, yeah, it makes sense. All right. Does anybody have any suggestions here for them? All right. No, that was very good, guys. I think you thought it through. That was good. All right. Let's see how this team did. Team 2, exercise 1. And it's right here. So you guys had the coffee machine. Okay.
Yep. So we went with the testing equipment, facility, obviously, coffee flavor replacement system. So you're gonna have to like replace the flavors in order to.
Well, I don't want you to, and sorry to stop you right away, but
Go ahead.
I don't want you to get confused. This is integration, right? So
Yeah.
there is an aspect of you bringing the parts together and eventually testing those. So I don't want you to think you're testing them. If you remember, one of the things you may bring some of the parts together and have some test equipment in order to figure out if that element works.
hmm
So you're not wrong in that one, but the replacement system might be more of a operations type thing, although you probably need to get it working, I guess, maybe. Is that what you're thinking?
Yeah, but I think you're right. Like it's more of an operations thing. So
Operations. Okay, I'm going to put that down. Okay, but I like your software integration, so that's good.
software integration system, temperature measurement system for the
Yep.
heating coffee, um, assembly line, assembly machine / robots, and
Yeah,
hot
no, that's good.
tubes.
Yeah, I'm just going to push that. Yeah, can I push that? Where's your push thing? I guess I'll just do this. Okay. So you have assembly machine. Okay, and COTS vendors, coffee filters. And what's interesting about that is you may have to integrate them in right away. Usually this right here might be an operations thing as well. So I think because I'm trying to think of how the coffee filters help you integrate the system as a whole. It is an enabling thing in operations. You need to make sure it's available, right? So you definitely need to do that. That was good. I know that was hard. Did you find it difficult trying to separate out?
Yes, very.
Yeah. All right. Well, that's why I had you guys work this. So let's see if Team 4, with their new member, was able to actually do even better. So, all right, Team 4. Oh, you have a long list. Okay, looks good. Let's blow it up a little bit further for you guys. Okay, go for it. Alden, I guess you're the one.
Sure. Basically just broke down to manufacturers. So, the blades, the frame, the charger, and all the components that add into that. And then we have the manufacturers for the pomegranate granite features itself, for the other features that will play a factor in the life cycle.
Oh yes, right. I see what you're saying. You're worried about the product as a whole.
As a whole, yeah.
Yeah, gotcha. Okay.
Then you have the features in general that need to be broken down, but of course we're going to go into that. You have the manufacturing robots, the ones that are building, the blades and the plastic frame through automation. You have the user manual. Yep, the operations of it. Measurement tools that you kind of identify to us, which include blades, measuring the blades. We have to measure the frame to ensure
Make
that
sure
it's
it
the
works. Yeah.
exact size. We have to scan the blades and the
Yep.
frames
That's good.
in order. Also, the charging unit analysis.
Yeah.
Sure the voltage is correct, the batteries is correct, and they're not, dead or what have you. So,
That's real good because a lot of people don't really, right? When you're in a manufacturing scenario, a lot of times you want to go out and just kind of test something rather quickly to make sure it's within spec, right? So that makes sense. The only thing your manufacturers, I'm trying to think, that's helpful for implementation. But I'm trying to think of how, there really is a blending of implementation, integration, verification. You kind of blend all those together. It's hard to just have a hard stop and say, hey, I'm worried just about integration. You can't ignore everything else. So,
Yep.
So I don't want to dissuade you from this, but I would kind of put this underneath more the implementation, implementation enabling system, as well as user manual would be operations enabling system.
Okay.
So, all right, good job, guys. Good, very good job. So, so that's what I kind of got you guys thinking about integration, what it takes, the enabling systems. One of the more important aspects of the enabling system, thinking about them ahead of time, is being able to ensure that they're available when you're actually doing the integration. You don't want to be halfway in trying to get some cabling to match up, and you need some kind of device to help guide those cables, and you have to buy it like quickly. And it's like maybe it had to be built. So that's where thinking about these things up front is extremely important as a system engineer. The other thing we worry about is the whole idea of interfaces. So we covered that in the design aspects of things. We covered interfaces as well as n-square diagrams. If you remember, we discussed what they were, how they operate. One of the things I basically showed you is not only the basic rules of the n-square chart, where all the functions are kind of in the diagonal, and you have outputs that are horizontal and inputs that are vertical. But also that when you don't have an X or a mark within those interface aspects where they interact, that means there is no interface there. And of course, don't forget your external systems as you go forward. So if you recall, I talked to you about what the various, if you actually take an n-square diagram and put it down into its parts correctly, you should be able to figure out if it's an isolated element, in other words, it doesn't interface with anything else, or it's a source that applies an output into the other systems, and you may even have a connector subsystem that connects two system sub-elements together. Let me just show you a quick example. I have like 9 interconnected functions. If I were to look at that from a very high level standpoint, I can actually add the across how far away each of these interfaces are from the various nodes. And I can just do that for each and every one. You'll have to do this when you do your homework. One of the first things I ask you is to score the chart I give you, and I give you something like 14. You should be able to go in and say 1, 2, okay, that's 1, 1, 2, 3, 4, 5, 6, add that. So it should be fairly easy for you. For this one, I gave you, it's 86. Now, what you could do is start manipulating the chart. Let's say I'll take A and B and flip it, or I take A and C and, you know, keep taking A down the thing and keep looking and you know, trying to figure out, am I getting a better scenario in terms of the actual chart score. But you'll notice that as we go through it, my score is not changing very much because I'm only doing one at a time. And if you were to run this through a computer and actually do combinatorics, you'll find that to be able to do this, you have to do like 181,000 times. You know, it's a huge amount of effort to make it work. Now, there is a way you can actually work this by actually looking for patterns, and that's kind of what I want you to do with your homework, is you actually will go in and actually start looking for these tightly related functional groups. I'm going to show you how to do that. Once you kind of identify them, you kind of put them all together, and then you reorganize it with that, what I call TRFG, and try to make sure your interfaces to the other components, that integrity of your interfaces are maintained. And then you start isolating the various subsystems as you pull it together, and you start repeating the process until all your tightly related functional groups are found. And then you should be able to reorganize your chart so that the source is at the top, the designations at the bottom, the various middle pieces, and you should be able to reduce the score of your chart fairly significantly. So let's look at my example I gave you. I actually find that if you get A and C together, and I believe it's right here, A is coming in. Notice it also interfaces with G, and it interfaces over here with I. So I'm noticing that A actually interfaces with them, and then C doesn't go back, but G does, right there, and I does. So actually, A, G, and I are actually what you would call TRFG. So I would take G and throw it up here, and I and throw it up here. And so if I were to actually do that, well, I threw it at the bottom. I would throw it on the bottom. I'll notice that I can now collapse that because they're all interrelated with each other. And all I have to do is make sure I don't lose the connection to D right here and the connection to C over here. So notice I was able to combine those. Now, if I left that out so that it was a thing, you probably could see it better. But what I did is I went ahead and collapsed them. So I can do the same for the next one I find, collapse it, and make sure I maintain the interfaces. Now, the reason I'm going slowly with this is because when you do your homework, you may collapse them, you may not, but maintaining those interfaces are very important. So you always go back to your original and make sure that the various interfaces, and I put them in red, that I'm not losing them as I collapse them or even move the various parts around. So I do it one more time. C, E, and H can come together, and now I have three of these things. But I notice HEC actually has no output, so that's kind of at the bottom. And what I did is I actually went probably a little too far. I actually collapsed them that way. Now what you have to do is you actually have to put it all back together again. And if you do it correctly, you'll notice that I actually probably would have had these two figured out and this one figured out, and I would move them around inside so I get these tightly aspects. Now, let's go ahead and actually add this one up. I actually come down to 28. So I went real quickly, by using this technique, I went from I believe it was, let's find out, 86 down to, just by doing these various tightly integrated things, I really did about 3 in order to make it work. I'm down to 28. So that's kind of the way to make this work. And what I want to do is actually try to get you to actually work on an exercise where I'm actually going to give you a chart like this, and I'm going to give you a few minutes to figure out what are my tightly controlled ones and how would I move them in there. You should be able to arrange them and look for subsystems in order to make them work. So I actually did the first one for you, maintain the interfaces. So I'm going to walk through this, but before you do that, actually, did I already give you the answer to this one? Are you guys going to go ahead on me? I just realized. How many of you know the answer to this one? You guys there? You can come off mic if you want. I just realized I may have. All right. Oh, wrong one. I gave you the examples, so you can actually pull those up. Darn. Do you guys want to do this or not? Do you want me to just go through it? I just realized I probably shouldn't have gave you that example. How many of you downloaded this here? Or looked ahead in my slides? My slides gave you away, right?
I didn't look at it, but I think it would be beneficial if we just go through it because
Yeah.
I'm not
No,
that
that's
sure to understand it yet. But yeah.
Yeah, no, that'll work. All right, let's do that. All right, let's do that. All right, so what I'm going to do is just walk through. I wanted you guys to do this as a group, but maybe it'll be better if I just show you, and then I'll show you the homework, and I kind of want you to go through these steps. All right. So first, you arrange. Well, I already give you the n-square chart, so that's fine. You just need to go ahead and score it. And then you start looking for those various TRFGs, starting with the very top. And then, of course, you maintain your interfaces as you're going on. So you can actually take this one and you say, well, I want to take this F1 and throw it down with F3. So notice I actually got a little subsystem there. But the one thing I have to make sure is your F1 is, and once this is together, it talks to F2. All right. So notice I actually have F1, F2 here, and I maintain, F5. So I actually maintain that interface right there. Right. I combine them, I maintain the interface, and I made sure it works. Okay. So now I'm like, well, what is F2? Is there something that I can use? Well, it looks like F7 and F2 are a very good candidate for their TFRG. So I put that together, and I actually notice, okay, when I combine them, okay, I notice I don't have anything. It's actually an isolated component. It's actually not talking to anybody else. So that's probably good to know. All right, so I can move that up to the thing. Now I start looking at F4. I'm like, whoa, there it's really contacting these others quite heavily. And I have this F6 to F5 working. So I actually, once I combine them together, you'll notice if I move some of these, I can move this one over slightly. So I actually do that. So I combine them, and I noticed that it probably should go ahead and get moved. So I actually moved the isolation one up there, no interfaces. The source I put up there, it communicates with F5, which communicates with the designation. Okay. Now I'll take this and break it out into the actual 9x9, the original. So here I have the isolated up there. I have the source. I have the F5, and I have the designation at the bottom. Notice how tightly integrated it is. So once you start adding these up, you're down to 14. So you actually can expand and do that calculation. So in your homework, a lot of students fail. They kind of stop right here and don't expand. And so it's important you expand and then just double check your interfaces here to your original, right? So if you look at the very original, this one, F1 talks to F3, you go back and make sure that that's the case. So when you start, because a lot of people, students fail making sure their interfaces match what I originally gave you. All right. And of course, you can analyze the interfaces at that point, and you're able to actually come up with your IDEF 0 a lot better once you have a good understanding of what the systems are. But these are just some of the ways to go about this. Now, I want to see if you guys have any questions about what I showed you here. Get rid of that.
Yeah, I got a quick question.
Shoot, please, too. Shoot.
Can you go back to a few slides to
Oh,
where
yeah, absolutely.
I think F1 and 3 were merged?
Yes, right here.
A little before that.
Oh, yeah. The first time? Yes.
Yeah, so like F1 was talking to F3, I understand that, but F1 also talks to F5. And so when you preserve that interface, it just seems kind of confusing because F3 doesn't talk to F5,
But it's one system now.
but okay, so when you merge it to one system, they both then talk to
All right.
F5. Is that what you're saying?
They will, right? Because it's you kind of combined them, right?
Okay.
But notice that when I get to the end of the final system here, F1 does talk to F5.
Oh, okay.
And F3 doesn't.
Yeah.
Okay. So with that in mind, you may find it a lot less confusing if you don't collapse these things. This is kind of a technique. And I actually give you, if you recall, well, maybe you guys haven't looked at all your things here, but I actually have, where did I do this? Up here, well, that's your assignment. Oh, back in the, I'm sorry. Let me go to the class folder. Let me turn this off. If you go to class 9 here, right, in your lecture notes, oh, I thought, well, maybe I don't. I thought I read ahead and quiz. Optional readings, I actually have several readings that talk about n-square charts and how to work them. So the method I showed you is one method. It works fairly well. But you may find yourself, why don't I just keep F1 and F3 together up on the top, and I'll just try to rearrange them that way. You may find that's an easier way to maintain your sanity as well as what your confusion, like you're saying. Does that make sense?
Yeah. Thank you.
Good. No, I want you all to do well on this homework. It does take a little bit of effort, especially in the fact that you're moving things around on either an Excel spreadsheet or a Word document, whatever you're good at for actual charts and stuff. It does take effort to try to make this work. So one of the things I did give you, I give you the choice when it comes to the assignment. Oh, the assignment's not up yet? What the heck? I'm going to have to, it'll probably come up soon. It's 6 o'clock. Oh, it's hidden. Oh, I'm going to have to unhide that. It's assignment 4, right? Okay, it should be available now. Okay, so when you go to assignment 4, I give you an Excel spreadsheet or a Word document or a PowerPoint, depending on what you're good at in terms of manipulating the things. But I don't want you to get discouraged. If you want to do it by hand, I've had people do that and take pictures. But what might be nice if you did that, put it in a PowerPoint and create a PDF so I can see it. That'll be good. Usually a PowerPoint PDF is fairly easy. The Excel spreadsheet, I don't want to just see your beginning or end. I would like to see your work. So be sure you know how to do a PDF for the entire workbook and that you're scaling it correctly. All right. Does that make sense? I think that's all I have for you guys. You guys can go off and get to work. I can get you guys out early. Is that okay?
Sounds good.
All right, good. At least one of you came through. Good job. All right, guys. No, I really appreciate you listening to me. Let me make sure I don't have anything else in here that I don't want to. Okay, so that's you. So read. Don't forget the quiz and stuff like that. But don't forget your team project. You have a plan for your for the test readiness review. So start working that as you're doing it. So next week we'll be doing verification. You don't have to, you're not due for homework 4. You have 2 weeks to do this n-square chart. You may find it challenging, especially with the tools you're given. If you're not experts at the tools, I challenge you to get good enough to be able to show your work. Learning these tools in any type of environment is helpful for your career, so do your best to learn them that you can. All right, and we'll talk about verification. So you should know where your grade is at now. You've done your midterm. You only have a few more homeworks left and one more TRR. You guys, most of you did very good for the CDR. I appreciate that. So from a class schedule, we should be able to present the TRR before December. All right. By the way, I have a question for you. I think Precious may be alone. I'll contact your teams. She may need help with the TRR, and she may, if you feel you can take on another teammate, could you let me know, and we'll bring Precious into your fold. I'm sure she'll bring some good.
She could join us if she's alone. It's okay.
All right.
Nobody to struggle or suffer.
Okay, thank you. I appreciate it.
Yep.
All right, Precious, does that sound good to you? Is your mic working for me, or maybe not? Give me a thumbs up or a high five or something. Sorry, Precious. I know you're trying to get it to work. All right, there you go. Good, thank you. All right, so what I'll do is I'll make some of those changes in there. I haven't heard about your teammates yet. I assume they're going to drop out because neither of them did the midterm. So assuming they're dropping out. So that in mind, thank you guys. If you have any questions, send me an email and we'll talk some more. I'll hang here as you guys hang up if you have any extra questions. All right, so you guys can go off, do your homework. I'm sure you have other things to do. So we'll see you guys later.
All right, thank you.
Thank you. We'll see you guys.
Thank you.
Bye-bye. We'll eat some pizza while you're working.
Yeah, Professor, I got a question.
Yes.
So I posted earlier in the chat. Yeah, so for the voice translator, I was not able to figure out any testing service. So with that, the software testing program would be counted as.
Oh, no, right. No, you're fine. We're going to talk about verification and what that means.
Mm-hmm.
You'll actually be in the position where how do you test a complete system that your voice translator will work? So you'll have to think about what kind of program or a simulation or something to make it work. And that's actually something I meant to talk about is simulation. So you're right. I should have talked about more of that. Um, but the simulation of the whole pomegranate system, and then you put your element or subsystem in to make sure it works as a whole. So,
Okay.
so I think you're fine. You're
Yeah.
fine. Okay, Rohit.
No, it's
Okay.
good. Yeah.
Okay. Keep
Okay.
doing well out there. You guys doing great.
All right. Thank you.
Okay. We'll see you. Bye bye.